Okay, it's close to 8 now. Let's get started. So welcome. This is our lecture number 3, Tuesday morning, September 1st. And let's start out with any questions on homework statements itself. I had a few come by or email already about some clarifications, but everybody good so far? Hopefully, of course, especially at the beginning, should be a lot of repetitive stuff, maybe some other things you haven't quite done before, some transformations. There was one question about MRPs to CRPs, so we are looking for a direct transformation. You may use quaternions or Euler parameters as stepping stones in the middle, but in the end, you should have an analytic answer that goes from CRPs to MRPs or MRPs back to CRPs. And in fact, I think they're on the slide that I've had in class, so you kind of see the answer already. What I'm looking for, as always, is the path. How do you get there? How can you solve all that stuff? So it's kind of a warm-up question to get through that. So first 2 lectures, or actually about a lecture and a half, because half of the first lecture was just introduction to the class. We've covered about 5 weeks worth of kinematics. All right. So now we're going to continue with this pace this week by covering some of the dynamics, and we're going to cover some of the basics of feedback control, you know, Lyapunov theories, all this kind of stuff, to get everybody up on the same page as we go through this. So we're going to continue to move fairly quickly this week, then we will slow down in the pace as we get into new stuff. We won't be quite continuing at this pace. So this is assumed to be somewhat review material. If you're kind of fuzzy on some of these things, definitely stick on top of it, go back, look at examples to get all that going. Okay. So moving on, this is essentially chapter 2 stuff that we're going to review here first. Chapter 2 talks about the motions of a single particle, then a system of particles, and then the system of particles becomes a continuum. Continuum could be blobs of jelly, beans bending, all kinds of general stuff that happens there. But we just have, you know, a continuous thing that sets it off. What are some of the highlights that we should remember from this stuff? Keith?
Highlights from just continuous.
Yep.
You mean like what properties, like kinetic energy or?
What is kinetic energy of such a system? Do you remember?
What is it?
Mm-hmm. You know, do you remember the formula?
1/2 mr squared, or r dot squared.
Okay, so r dot is what here?
It's the velocity vector.
With respect to?
In the inertial frame.
Yeah, it's inertial derivative of the position vectors, right? You can add them. Now that's for one particle. What if we have a system of particles? Billy?
I just take the integral over all the particles you have.
If it's a system of particles?
I guess it's the sum at that point.
The sum, yeah, so the next step would be the summation of particles. Instead of just one, we have 60,000 particles contributing to the energy, so it's a big bookkeeping problem, right? It looks much more complicated all of a sudden, but really it's just a bookkeeping problem, fundamentally. Now, where do we take an integral, Billy? What kind of a system?
Usually for rigid bodies? Or
Rigid is one form of that.
just the continuous
Continuous body, yeah. So there's blobs of jello, same kind of a thing. So you can't discretely say there's a bolt, here's a bolt, there's a bolt. It's just a continuum of mass. And this will impact when we do second half of class, go back to analytical mechanics. We'll start out with particles again and then end up in the end with partial differential equations where it's continuums of things. So this is a good review to kind of get thinking along those lines again in this stuff. So good. So energy, there was energy stuff. What else was here, Joanna?
The superparticle theorem.
Superparticle theorem. What was that one in plain words?
That the motion of the center of mass. Wait.
You want to say it with confidence. 2 weeks.
Yeah.
No pressure.
The force equals the sum of the mass times the motion of the center of mass.
Is equal to?
The force.
Which force?
Acting on the entire system.
So if I have a spring mass system that's bobbling, so 2 masses and a spring connected, do you include the spring force?
That's a
Joe?
Depends what motion you want to see.
So if you,
We're talking about superparticle theorem.
yeah. So for the superparticle theorem, you take all the mass in the system, and then all the force on that mass, and the total force on your system mass divided by that system mass is equal to the acceleration of the center of mass of that system.
Okay. So again, my question stands. If you have a spring mass system, Billy, would you include the spring force?
No, because it's an internal force. We only care about external forces with the superparticle theorem.
Yes. It's a net external force act. All the internal forces, once you sum them up, as you're saying correctly, so if you did your approach, you would get the right answer. You're just taking more steps than you'd need.
Sure.
This class, especially the second half, is a lot about how lean can you be in your approach, right? How fast can you get from A to B? And then you would be summing up stuff that's going to cancel out anyway, right? So it's very critical that we start to really practice on what can we include, what can't we include. So superparticle theorem, it's basically the total net external force acting on the system is equal to mass times acceleration. So the center of mass of any continuum, of any system of particles, and of course for a single particle, it acts like a particle. It's, you know, even the blob of jello doing weird stuff, spitting up other blobs of jello, for the system, the center of mass will act just like a particle. If there's no external force, then if this blob goes off, this other part has to move off, so the center of mass stays the same. Right? It has to be invariant if there's no external force. At least be inertial. It could be drifting at a constant rate. So good, superparticle theorem comes in here. Yes. We talked energy, and we talked energy. What other quantities do we always have to talk about for systems, dynamical systems? Sarah?
Momentum?
What kind? We have two kinds.
Linear and angular momentum?
Right, so linear momentum, angular momentum. Those are kind of the classical things. And with energy, there's one other form of the energy equation that we keep looking at. This will be important for proofs and stability and other kind of stuff. Besides energy, what's the other equation I keep pestering you guys about?
Change in energy?
Yes, the power equation, yep. Because why is that important? When we do Lyapunov control, right, Lyapunov functions often based on energy-like expressions, so there may actually be energy. Understanding how the energy rate comes into play, that can really help you. And we'll be looking at that. Again, second half of the class, we'll be talking about forces being working and non-working forces. This is basically, do they change the energy state of the system? And that's going to be important there as well. So, kind of a practice. So we're going to move through this. Again, I'm assuming you've seen this, otherwise I would never be going through this at this pace. But we're just going to hit some highlights, make sure everybody's back on the same page. So Newton's law for a single particle is just the force acting on that particle's mass times the inertial acceleration that you have. That means R has to be written relative to the inertial frame, and you're taking time derivatives as seen by that inertial frame. Right? F equals ma. That's basically what it is. This force vector, we often will break it up into external contributions and internal contributions here, in this particular formulation. And so if you need to have the total force, if this is a continuum, I'm skipping through the systems of particles. Just essentially for the systems of particles in the continuum, summations get replaced with integrals. So the book has a more formal treatment of that, but I'm going to save some time here. So the total force acting on this is essentially what Joe was saying, right? We have to sum up across everything. You're doing an integral across all the forces acting on each particle, and it's just going to be the sum of all the external forces. Anything internal, those things will always cancel out in the summation. So F is the total force. Then, the center of mass definition, that was another one of these continuums. Different definitions, mass times the center of mass location is equal to the integral of R dm. So in essence, RC is the integral of R dm divided by m, or that's essentially, if you think of it this way, you might have 2 kilograms 1 meter out, 1 kilogram half a meter out, right? So you do the mass averaged location of all those masses, and that's the center of mass. That's just one way to think of center of mass. Yes?
All
Kyle.
of these are assuming uniform mass distribution, right?
No, not here yet. This doesn't have to be uniform here. So if I had 5 kilograms here and 1 kilogram there, it just means my center of mass would be roughly over here. That accounts for it right away. Yeah, we don't have homogeneous stuff.
We never make that assumption in any of these equations.
Not in this particular steps. When we go to rigid bodies, we assume everything's rigid, and then it depends how you compute your inertia, basically. It all comes out of the inertia computation. If it's not a homogeneous cylinder or box, then you'd have to account for that in how you compute your inertia. Yeah, so it's kind of embedded within that step. But here, yep, center of mass. So this is one of the center of mass properties we can exploit. There was another one that would turn out to be very, very handy. Who can give me that one? because here you have some inertial frame, you have some particle, let's just call it, let's say we're doing continuums, so that's a differential element there, R. There's a center of mass of a system, right? And then there's some blob around it. So the total mass times RC ends up being R times dm. There's a differential mass. What's the other version of this, Gabrielle? Do you remember?
You define R as RC plus little r.
Good, okay.
And then,
So now, instead of using the inertial location of that infinitesimal mass, we use its position relative to a center of mass. Good. What happens next?
I'm forgetting.
Let's just plug this in quickly. All right, we've got mRC equal to R ends up being RC plus little r dm, and that gives me RC dm plus r dm. What is RC dm going to give me, the integral of that, Franklin?
Then mRC.
Yeah, RC, does it vary with each mass location? Because for this continuum, every part of that continuum has to have the same center of mass. So while the center of mass itself may vary with time, as seen by this integral, this is an integral with respect to time, this is an integral over the body. Everything has to add up to be the same. So this is nothing but a constant. Right? It was one of the arguments we made in 5010. So this is really, if I do it explicitly, that's RC times the integral of dm, which is just the total mass. All right, so this and this cancels, so 0 is that. All right. So the mass average location relative to the center of mass has to be 0. That's essentially what you're seeing here. It's one way to think of it. Whereas this is the mass average location relative to an inertial frame, gives you that, this is where the center of mass is relative to inertial frame. Yes, Joe?
Question. And this is, if you took a time derivative of that equation.
This one?
Yes. So the left side isn't very interesting. The right side you get integral of r dot dm, because it goes through the space integral.
Yes.
I am imagining, I guess since that's relative to the same frame. Okay, I was trying to see how that didn't violate a non-rigid assumption, like if the whole thing was expanding, or if the whole thing was...
Yep. So here you could take, this is just 0, and you're taking a derivative, which means here I'm taking the inertial derivative of it, just adding dots over it.
Yeah.
That's true. If you took body frame derivatives of this would still have to be true. You can take derivatives with respect to any frame, because derivative of 0 with respect to any frame is always going to give you 0, and you can expand different forms of that on the right-hand side. Now, what does this not include here? Benjamin?
What if the blob is moving around so that the domain of integration is not constant?
That would still work, because if the blob, then this continuum, the shape changes, the center of mass still has to satisfy these properties. This still works. But what's the key thing we're assuming here? I'm treating R as time varying. What about dm?
Oh, it's not getting heavier or lighter.
Right. So if you have a rocket problem, you'd have an extra term you'd have to account for. There, your system is literally losing mass. You could account, if you wanted to account for the thrust propellant being expelled, then it's all conserved. But otherwise, you're losing mass, and you'd have to account for that there. There would be a mass rate that comes into this as well. And that's essentially the rocket equation. I think chapter 2 also covers that one, if you want to look at it. We're not looking at objects losing mass in this particular class. We're looking more at the other dynamics. That's what we're going to focus on. But good. Quick review of center of mass properties. This is definitely one fundamental. It's the center of mass is always the mass average location, either relative to inertial, which gives you this, or relative to the center of mass, as Gabrielle developed, and that's going to give us this simple form. And that's going to be very handy when we do these other simplifications. So good. So center of mass. Now, I can differentiate this twice, the center of mass property. That means mass times the inertial acceleration to center of mass location has to be equal to r double dot dm body integral, but r double dot dm is nothing but the force acting, and that's mass times the inertial acceleration. That's going to be the force acting on it. So the body integral of that, which means this is now the superparticle theorem. So we very easily, quickly derive from the center of mass property two derivatives, plug in F equals ma, and you have the super of mass property defined. Yes?
Why isn't that external force in there?
The sum of the external forces?
Yeah, isn't that usually how Newton's second law is?
Yes, this is written a bit more generally. F is being this total. It arrives as the total summation of all the forces, including internal. In the end, this ends up being the net external force acting on the system. Yep. But you can think of that as a refinement of this. As we derived it, we didn't have that other. I mean, you could replace this with this and then just call this, well, it's still F as we defined it. It's the same quantity. So different ways to think of it. Good. Okay. That kind of gets you guys thinking. Now, kinetic energy. Keith's favorite thing, right? 1/2 mass times velocity squared. That's it for a single particle. And you'd have Ri dotted with Ri, because we need to get the velocity magnitude squared. To get the velocity magnitude, you dot the vector with itself, and that gives you the magnitude squared. That's exactly what we need. So that's the velocity vector dotted with itself, gives me the velocity magnitude squared. That's it. Nothing more complicated. And now instead of a summation, I have an integral because I'm doing it for an infinity of infinitesimal points. That's kinetic energy. Now, r dot, following the similar stuff, this is not very useful in this form because it requires us to recompute this as the object moves. I get new positions and it gets much more complicated. I have to do the integral every time. So r dot itself is rc dot plus little r dot. Little r defined relative to the center of mass. And you plug this in. You should be able to do this on your own. Do the dot product, carry out, you got a sum of two vectors dotted with a sum of two vectors. You carry out all the possible combinations. You will end up with an rc dot dotted with itself, an rc dot dotted with r dot, and then an r dot dotted with itself. And you can see there's two of these, and the dot product commutes. So a dotted with b, same thing as b dotted with a. So you can add those two up, and that 2 times 1/2, and it drops out. Again, here, RC dots, RCs don't depend on the body integral part. That whole body has the same, every point in that body has the same center of mass, otherwise it wouldn't be one body or one system. So you can take them outside the integral, that just becomes total mass. This pretty much stays as is. What happens to this term now? Elena, do you remember? What happens to this term?
Well, the body integral of r dot is 0.
R dot dm is 0. Yes, right. So because of the center of mass property, this part drops out, and that leaves you with this kinetic energy expression. This is for a continuum now. We haven't frozen it, made it rigid. So this is nice because it essentially says, okay, the kinetic energy, instead of doing this stuff, I can break it up into two parts. This is the kinetic energy of the center of mass itself, plus the kinetic energy about the center of mass, where we've taken all these positions now relative to the center of mass and looked at the, but it's still the inertial derivatives of R, not the body frame derivatives of anything. But that's how this works out, right? And this is good for any blob, jello, anything that happens there. So good, work energy principle. So Kyle, we're talking about power equation, right? The derivative of energy. What does work on a system? And this will be important several places in our class this year. So we had kinetic energy expression. That is weird. Okay, I'm getting some wobbling here. Which is, if you go back, this one with chain rule, I'm going to get r double dot dotted with r plus an r dotted with r double dot. Again, dot products commute. So it's 2 times r double dot dotted with r, and the halves cancel out. So you end up with this, plus the same thing with the other part, right? We've broken it up into 2 sections. And now we can start to substitute things. Mass times the inertial acceleration of center of mass is the total force acting on the system, total external force, if we want to be more specific. R double dot is big R dot, double dot minus RC double dot. You can plug that one in again. And let's see, you end up again with an expression here of R dot dm integral. That one's going to cancel out. And we're left with this. This is nothing but df, mass times the acceleration of that infinitesimal element. That's just going to be df itself there. And we end up with this expression, which your power, from a translational point of view, tends to always be force dotted with the velocity at which the power, that force is being applied. And the same thing holds for the infinitesimal elements. So that's the force acting on that infinitesimal element dotted with the velocity relative to the center of mass. So we could break it up as we did there. So now we want to figure out the energy change between two time steps, which you can do two time integrals, right? Integrate t dot, the energy rate from t1 to t2. Or you can also rewrite that. You can do a substitution here where instead of being a time interval, you can actually write it as a position interval as well. The classic calculus stuff. You can go look at that and see how you can do that. And then, so now it's force, the energy change ends up being roughly the integral of force times distance traveled, ultimately. Right? If you have a constant force, then the integral from here to here is just delta r, the distance traveled. And force times distance traveled, that's kind of the classic high school level you've probably seen of energy changes that happen on these systems. So, different ways you can write these things. Continue. Linear momentum. Now, one way to write linear momentum is mass times velocity, right? That's your linear momentum. So P, the total linear momentum of a system, is the integral over all the infinitesimal, however things are shifting and moving, and then you put that in. Now we do the usual expansions. R becomes RC plus little r, and everything has dots on it, and we can see that this one quickly is going to vanish again. We have the integral of r dot dm from center of mass property. This RC dot you can take outside, and you just have the total mass. So the linear momentum of a continuum is simply the total mass times the inertial velocity of this, mass times velocity. It still works, even though it's a weird blob continuum system. Linear momentum has to satisfy these equations. Now, F equals ma is actually one way you can write this, especially if you're doing the rocket equation. You don't do F equals ma directly. What it really is more fundamental is that the inertial derivative of linear momentum is equal to force. So the inertial derivative here ends up being, you add a dot, mr, which form am I going for? I'm using this form, so I've differentiated this to get here, and then again replace that with df. You can see the linear, quickly you've proven here that the inertial derivative of p ends up giving you the total force acting on that system. So this is like superparticle theorem version of linear momentum. If you have no external forces acting on the system, then the linear momentum has to be constant. In fact, the center of mass has to be moving at a constant rate. The body might be deforming. Some parts, astronauts may be moving forward, some moving back. That's fine. You're distributing mass, all with internal forces. But there's no external force acting on the system, so the linear momentum of the system has to be preserved. So if you're doing integrations of equations and testing these things, this is something, some of those integration tests you can do. Make sure this quantity is preserved. So that's basically what it looks like. Let's just go back quickly. How do we get F equals ma out of this stuff? The linear momentum of the system is here, right? P is equal to this. And if you differentiate this, you get P is equal to m times RC double dot, assuming m is constant. If m is not constant, you'd have an m dot in there. So F equals ma is true if mass is preserved. If mass is not preserved, this is a more rigorous fundamental property of one of Newton's equation, that the inertial derivative of linear momentum gives you force. The angular equivalent of that is what? Benjamin? The inertial derivative of angular momentum gives me what?
The torque from the external forces.
Yes, very equivalent, all right? So H dot equal to L, that's what we had in 5010 a lot. So the inertial derivative of angular momentum is the external torque acting on the system. That's what we needed. The inertial derivative of linear momentum is the external force acting on the system. Works for continuums. So good. So angular momentum, I'm writing this one out. If you take angular momentums, the one extra thing you always have to worry about is about which point are we taking the moments, right? Which point are you taking? And that's really arbitrary. You get to set this up. I'm summing up all the moments about to this point. And this point is inertial, or it's body fixed, or it's the center of mass. And depending on what it is, you get different forms. So here I'm solving it once and for all, where I have a point P that's generally somewhere. It could be the center of mass, it could be attached to the body, or it could just be floating in space, or accelerating, or whatever it's doing, all right? So I have the moment arm is this position vector minus RP. So that gives me this vector sigma that you'd have, right? And angular momentum is basically, you always got position crossed with linear momentum. And in this sense, linear momentum is mass times this velocity of sigma, the time rate of change of sigma that you have. So you write these things out, you get the a vector crossed with itself, which would be 0. You get a sigma double dot. Well, sigma double dot is r double dot minus rp double dot, which we plug in. Rp right now is independent of this body integral, so it's outside. And so that gives you that term. This term now, I've just expand r minus rp again in here. You write these things out. The integral of r dm, that's the center of mass definition. That was nothing but mass times rc. And the integral here, it's just the integral of dm is mass, so you end up with mass times rc minus rp. So you can plug that back up in there. The next thing we're going to look at is what happens with the torque. The torque about this point P is always going to be the force at this point, which is mass times acceleration. That is the force. The moment arm crossed with that force. That's one way to write it. And let's see, up here we did see a sigma cross that. That's basically going to be your torque expression. So plug that back in, you get this plus this term crossed, yeah, so m times this crossed with rp. So that's what gives you this extra stuff. So here is, earlier we just said the inertial derivative of angular momentum is equal to torque. There's a disclaimer on that, some fine print, right? Only when is that true for this system? Joe, what do you think?
P is inertial.
Okay, so if P is inertial, why does this term vanish?
Because the double dot, yeah, P is inertial, the double dot has to be.
RP double dot has to be 0, right? That's the definition of being inertial. There's no inertial acceleration. Good. What's the other way we can make this second term vanish, Elena?
Center of mass.
Center of mass. If RP is equal to RC, then this whole thing vanishes, right? So this is a key thing then. So only if you're taking moments about the center of mass or about an inertial point, it's h dot equal to L. And that's typically what we do. But sometimes you might get into an off-balanced wheel problem or the kind of stuff, and you might have to be more general here. Or looking at flexible body dynamics in my lab right now, then we have to actually account for these extra terms, because we're taking moments about a body fixed point, and that's not the center of mass. So extra stuff appears. But otherwise, this is good. This also means sometimes you can write this out and get different expressions, depending if you're solving a problem dynamically. You can write, like in 5010, we did the falling rod problem, and you found you can do h dot equal to L about the center of mass, and then certain things act, but the gravity force doesn't do a torque about the center of mass, because it acts on that point. But you can also do h dot equal to L about the origin. And then, for example, the reaction force of whatever the hinge is doesn't apply torques, and it's easier. So sometimes you can write out both versions of this h dot equal to L and get useful information out of it, right? So it's a very handy equation that we use a bunch. That's it for continuums. Now we're freezing them. So now we're moving from a continuum blob to a rigid body. What is the key thing that changes here?
Transport velocity.
Be more specific. What specifically changes in these math expressions we saw?
R dot becomes omega, R cross omega.
Almost.
Omega cross R.
There you go. One or the other, right? So why is R dot not 0 if the body's frozen? Why isn't this location of this mass relative to my center of mass? That's the center of mass here. Why is this derivative not 0? It's always at the same location, Billy.
It is in the body frame, but not necessarily in the inertial frame.
Exactly. That's the key. So as we're freezing things, and there was a question in the first lecture, why do we do body frame derivatives and stuff? Again, this is a case where it makes your life so much easier. You can do inertials, but then it's much more complicated in writing it out. But essentially what's we're doing here. But in the body frame, if it's a rigid body, then the right wing should always be to your right, never to your left, or your plane has problems, right? They're no longer rigid. So that's the key assumption. R dot is going to be equal to the body frame derivative, which is 0, plus the transport theorem. That's the omega cross R. That's why it was omega first, omega cross R in there. Yep, okay. That's it. That's basically how everything gets refined. So the angular momentum here about an inertial origin O is R cross linear momentum, same as what we just saw. Instead of with sigmas, we have now explicit vectors here. Or I'll leave this up to you. You can plug in R is equal to RC plus little r. It's a good thing you should be able to do in your prelims, for example. Can you write this out, and then you can break it up as the angular momentum of the center of mass, and then the angular momentum about the center of mass. Same thing what we did with kinetic energy. We were able to break it up into these two terms. And that's very convenient, because the angular momentum of the center of mass, especially for astrodynamics, this is typically your orbital motion. And in this class, we're focusing on the attitude side. How do things tumble? I don't care as much about the trajectory. I'm caring more what's happening to the attitude rotation history, right? So we are going to really focus on the second half, typically, in this class. So that's the angular momentum about the center of mass is little r dot dm. Now, as you guys said, for rigid bodies, this is not going to be 0, but in fact be the transport theorem, and this is the term you can set to 0, the body frame derivative, not the inertial. So we still have an omega cross r that you plug in. Now, if you do that, you end up with this omega cross r, which is the same thing as minus r cross omega. And r cross omega is the same thing as r tilde omega. And I have another cross, so it's an r tilde omega. What do we call this term in the end? Benjamin?
Inertia.
That's the inertia, right? And I call it typically inertia tensor. And like a vector, the tensors have a frame dependency. You have to pick a particular, this is frame independent. R is just a vector, magnitude times the direction. This all of a sudden turns it into a matrix representation of that vector. So I have to pick R components with respect to B1, 2, 3, or E1, 2, 3, and then you will have B frame components or E frame components of the inertias, right? So once you pick a 1, 2, 3 axis and the spacecraft's lined up like this, or you pick different 1, 2, 3 axes, you're obviously going to get a different moments, different inertias about those axes, right? It's still the same body. So good. So we can do this. This is our inertia tensor calculation. You pick a particular coordinate frame. All the inertias are about, all the moments here are taken about the center of mass. We're about to generalize that. And then why can we take omega outside the body integral? Leela?
It's the same for if it's a rigid body.
If it were a continuum, could you do that? If it's just jello and blob and doing this?
No.
No. Then all of a sudden, your wings, if you're looking at flexible structure, your wings, your solar panels could be flexing all of a sudden, right? And it has different omegas than what your rigid main hub does. So then it could be different. But because it's rigid, by definition, this pen, every point on this pen has to have the same angular rate. It may have different inertial velocities. As you're moving up, this point might be moving quicker than the point in the middle, so forth. That's the inertial velocities. The angular velocities are the same. Otherwise, it wouldn't be rigid. Something's out rotating something else, it's deforming. Right. So we can take this outside, which gives us the classic equation, h dot is equal to I times c, essentially. And I is defined as this inertia tensor. And if you go look at your sophomore level statics mechanics books, this is typically what you've seen at least in an engineering curriculum. I'm not sure about physics, if you've seen this. Chris, have you done this?
No, I haven't. I was in electrical, though.
You're electrical, okay. Oh, that's very different, too. So have you seen these kinds of integrals, this 3x3 matrix for a body with x squared plus y squared and so forth? No? Okay. I would definitely go, chapter 2 I think covers this, and then on to chapter 4 as well for rigid bodies goes through this. But basically that's your inertia. Have you done inertia dynamics before?
Basic stuff, yeah.
Basic, okay. Well, this is about as basic I can make it here, for at least. This is for a 3D body, and in this class we're going to have to handle 3D objects, because we'll have systems of 3D bodies that we're throwing all together. So the angular momentum, I omega, here I can express it in body frame components, and that's equal to this. So if I have no external torque acting on the system, what happens to my HC1, HC2, HC3 terms? Patrick? No external torque acting on the system.
Just constant?
That means these vector components are constant.
Yeah, I'll go with that.
H dot equal to L. What type of time derivative are we taking, Patrick?
Inertial.
Inertial. with respect to what frame are you taking vector components here?
It's on the body frame.
So are the body frame components? No. So these can actually vary with time, even when no external torque. In fact, we went through this. Torque-free motion was a big case we tested in 5010, right? And this stuff, Bob, and you might have precessions and nutations and omega 1s and 2s and 3s vary. And if it's axisymmetric, it's a sine and cosine, and one of them is constant. If not, there was these Duffing equations we found that you could actually solve, right? But so these components are thing. But again, they're not arbitrary. Since the magnitude of this has to stay constant, the sum square of these components has to give you the same thing. And in fact, we used that to make what kinds of plots? What were those called? Where we, for torque-free motion. Pole-Hode plots, exactly. That's what we're doing. Said, okay, that's a sum square of the body frame components. H1 squared plus H2 squared plus H3 squared has to give you a constant, and that turns into the sphere equation in momentum coordinates, right? And the energy expression in terms of momentum coordinates was an ellipse. So the resulting omega history came out of the intersection between an ellipse and a sphere, right? That stuff. All coming back, kinda. Okay. So angular momentum that we have of this system. This is one way to write it. Now here, this is stuff you can look up in a book. You can go look in a statics mechanics book and say, okay, I've got a cylinder, I've got a slender rod, I've got a sphere, I've got a box, right? And that's a primitive. And it'll give you these inertias, but it's about principal axes, which tend to be the symmetry axes of those objects. So if I'm looking at an object like this, right, it's got kind of 3 distinct dimensions, principal axes, it would be essentially your symmetry axis. That's what the book gives you. And it will give you this. Are the inertias that you get out of the book typically, are there 9 elements, or are there fewer elements that they give you? Franklin, what do you think?
If you are on principal axes, it will only be 3.
Yeah, they will only give you the 3 diagonal elements. So if you line up like this, then your inertia tensor just becomes a diagonal matrix in this case, right? Which is nice and simple. And often in analysis we make that assumption, because for any rigid body we can always pick a coordinate frame where that's true. Are the principal axes unique, Benjamin? Is there only one set of principal axes for something that has 3 distinct inertias?
Would say no.
Okay. If this is one set of principal axes, what's the other set then?
Well, you could do a 180-degree rotation about that axis.
Exactly. So there's about 24 permutations. You can go 1 axis forward, 1 axis backwards, and still satisfy the right-handed system, all this kind of stuff. So if you have one set of axes, you can still, it's not necessarily unique, you can still flip what's positive x, what's negative x, and you can go back and forth. So, but that's what you look up. Now, looking ahead, again, this is more supposed to be a review. Here we're choosing to take vector components with respect to this body frame B, and all the vectors are taken relative to the center of mass. What if we don't want to take the moments about center of mass? Maybe you have a solar panel, and what you need is the inertia about the hinge axis at the end of a panel, but the book tells you this is where the inertias are about the center of the panel. How do we go from this to the other one? Do we have to redo the body integral? No. What do we do instead, Joanna?
Parallel axis.
Parallel axis theorem. So that's the one, right? Where for simple 1D stuff, this was always plus mass times distance squared, right? And we have a similar form. It's going to be mass times distance squared, but the distance squared is more of a 3D version of it, which we'll have. What if we have a different coordinate frame? Instead of this body frame, often spacecraft have multiple frames attached. There's a sensor frame, there's a body frame, there's a docking frame, and all kinds of things, right? So let's say you want to switch from a B frame to a C frame. Do we have to redo the integral here, Billy? What do we do here instead?
You pre and post multiply by the DCM between the 2 frames.
Exactly, right? So as you did, if you have vector components taken relative to B, and you need them relative to C, you have that vector times the CB DCM, right? Maps it from one frame to another. So the vector is kind of like a 1D tensor. The inertia is a 2D tensor, so instead of using it once, we have to use it twice. Pre and post multiply. So that's just some highlights. Let's go through the slides. You're remembering some of this stuff. The book derives this, but this is basically the transport theorem. I'm using the RC tilde transposed form because it gives me a plus here. If I didn't have this transpose, I would have a minus here. I mean, this puts it in a form that looks like mass times distance squared. So, but R tilde is a skew symmetric matrix, so RC tilde transpose is the same thing as RC tilde with a minus sign. different forms you can find. But this is the inertia tensor you have about the center of mass, plus RC just has to be the offset. Now, I need not the inertia about this point, but about some other point way back here. And when you add these two up, now again, apples and apples, you have, if you're doing the matrix components and adding them up, if this is in the B frame, you need RC in the B frame. If this is in the Q frame, you need RC in the Q frame. When you do these RC1, 2, 3 vector components, right? That's probably the biggest source of error applying the transport theorem, is you're mixing up coordinate frames when you're adding up the contributions. Just make sure they're in the same one. And that'll give you the inertia here in terms of whatever frame you picked to express all these things, right? Now, if you need a different frame, at the end, you use the rotation matrix, like we do for vectors with this 2D tensor. You basically pre and post multiply, and with the two-letter rule, you know, if we're doing a vector, v in the B, FB gives me V and F. And the B's have to line up, right? Here, for the matrix, when we pre and post multiply, I need FB inertia in the B frame times BF. But I'm just writing here FB transpose, assuming one of them is given. But in practice, you may have one FB given or BF is given, and you just have to then plug it in, make sure the B's are right next to the middle part, and then you're good. All right? So there are little tricks how to remember which one gets transposed depending on which one's given to you. And the two-letter notation to me makes it really the easiest. I have no problems there. So now, this is derivation we did last time, and if you assume now in the F frame this thing is diagonal, and this is something you can do for any rigid body. You can always find a principal frame. It may not even be unique. There's different things we can do. Anybody remember what's the relationship then? If you have originally a 3x3 fully populated inertial tensor, which, by the way, is this thing symmetric or not symmetric? It's symmetric. If you go back and look at the definition, the off-diagonal terms are exactly the same. It's y squared plus z squared, y squared plus z squared. It's symmetric. Can somebody tell me if this thing is positive definite? Why, Kyle?
It's a diagonal matrix, and all the values are positive.
Well, in this form.
Yeah.
True. And it's easy to prove it's positive definite. What about this form? Your intuition is correct. It is positive definite. But what's one of the requirements for a matrix to be positive definite?
All the eigenvalues are positive.
All the eigenvalues have to be positive, right? And the eigenvalues for a rigid body will be positive. We haven't developed any imaginary weird structures that have negative eigenvalues all of a sudden. It's always going to be positive inertias, not negative inertias. Which makes sense physically. We're always adding up mass times distance squared for each little fundamental particle. Mass times distance squared, how can it ever be negative in a principal way? So anyway, so yeah, symmetric, positive definite. I'm choosing a new frame, also body fixed frame, where it's going to become diagonal. What's the relationship? How do I go from this one to this one? The F1, you know, F frame has F1, F2, F3. What are these? Anybody remember, Billy?
The eigenvalues of I.
Almost. Eigenvalues of scalars. F1, 2, and 3 are vectors. I1, 2, and 3, those are the eigenvalues of this inertia tensor. That's correct. But the F1, 2, and 3 axes that you have to pick end up being the eigenvectors of this inertia tensor. So you go to MATLAB, plug in the 43 by 3, you get the 3 eigenvalues. Those are the 3 things. And then you get associated eigenvectors. Now again, here this ambiguity comes in. If I have eigenvectors, MATLAB has no idea what problem you're trying to solve. It doesn't know that classically the one axis goes to the nose of an aircraft, right? It'll just, there's some algorithm point 1 to either be the right wing or top or up or down or forwards or backwards. It has no idea. So that's where you as a user have to come in and go, which one of these eigenvectors do I choose to be my first axis? And then you get to pick a second one. Do you get to pick the third one? Why not, Kyle?
Right-handed coordinates.
Exactly. Now the third one is hopefully what MATLAB gave you, or if not, it's a sign within a sign. It might give you plus that axis or minus the axis. So when you construct this yourself, you can't just have MATLAB do it all for you. You have to make sure you end up with a right-handed coordinate system. So F1 crossed F2 gives you F3. And if you rearrange how you're putting F1 and 2 in there, then of course the inertias have to be rearranged accordingly. All right? So just some subtle things there, but that's basically the relationship. The eigenvectors of this matrix stacked up in rows gives you the DCM. This is the one that goes from B to F, the FB DCM. That's the one we get out of the stacking of stuff. So, okay, So we don't have to redo the inertia calculation if we're taking moments by a different point. We don't have to do it if we use a different coordinate frame. Parallaxes theorem and how to rotate tensor components from one frame to another. Right, that's what you guys know. Now, let's get the equations of motion of a rigid body. We're back to h dot equal to L, right? We're taking moments about the center of mass, that's why there's a subscript C, and then this equation holds. And h is now a rigid body. So to evaluate the inertial derivative of h, I'm choosing to take the inertial derivative of h, not the inertial derivative, I'm choosing to take the time derivative of h as seen by the body frame. Leela, why would I do that? Why does that help me? Seems like I make the line more complicated. On the left side it was just h dot, now I have two terms.
Well, didn't you have h written in the body frame before?
No, I had h written as a vectorial part. So we had hc vector is equal to the inertia about the center of mass times omega. If you take the inertial derivative of this quantity directly, does omega change with time inertially? You have a general, tumbling body. Is there omega dot?
Is it torque free? Or?
I don't, just general. No, not torque free.
Then it can change, right?
Yes. So it changes. What about the inertia tensor? If you're taking the inertial derivative of the inertia tensor, is that, and it's a rigid body, is that going to change with time? Again, rigid body, I'm tumbling it. Does the mass distribution of this object change as you as an inertial observer?
No.
Gabriel, what do you think?
It would, because your principal axes are like...
Right. So if you think of the inertia really giving you moments, the second order moments, a mass times distance squared of everything, right? If you have this orientation or this orientation, here the moments are aligned in the horizontal axis. Here, all of a sudden, they're lined up in the vertical axis. So as seen by you, an inertial observer, the mass distribution, the moments are changing, right? There would be an inertia tensor derivative. Yeah, say that fast a few times, right? But as seen by what frame is the inertia going to remain constant? Anybody? The body frame, exactly. So that was the key reason why we've chosen here to use, again, the transport theorem, because here, if I take h dot c, you would end up with an IC omega dot plus IC dot omega plus IC omega dot, like that, right? And it gets much more complicated, because how do you get the IC part? Well, we have IC fixed in the body frame, but then you have to pre and post multiply times the DCM. So with chain rule, you will have two DCM dots, C dots, which were minus omega tilde DCs, all plugged in. And in the end, you always get the same answer. Hopefully, it's the same physics, but it's a much longer way to get there. Versus if I just say, what's the body frame derivative of HC? In that case, you just get IC this. Right? Because as seen by the body, the inertia tensor would remain fixed. So keep that in mind. H is a vector. The inertia tensor is not a matrix here. It's really a tensor. So it has a frame dependency compared to DCM, which is a 3x3 matrix. We represent the tensor in terms of a 3x3 matrix. The same thing as we represent a vector in terms of a 3x1 matrix. Right? So can anybody refine this body frame derivative of omega? What happens to this?
It's the inertia derivative, because they're the same.
I agree. Now why is that, right? The inertial derivative, just writing it out, ddt of omega ends up being ddt of omega, and seen by the body frame, plus omega bn crossed omega. Why is this term dropping out, Elena?
Because you're crossing it with itself.
Right. So omega here, if you just write this, it's typically shorthand for omega b relative to n. Just gets a little tedious to write it out all the time. if you're doing control, especially if you're doing tracking problem where you have omega b relative to n, omega r relative to n, then you omega b relative to r, I would recommend actually just writing it out. It's easier to keep track of until you really feel comfortable with that. But not exactly. So this term here is just going to drop out. So that's why. The omega vectors, the angular velocities of q relative to r, the q frame derivative and the r frame derivative will always be the same. Right? That's what we're using here. So that's a nice thing to remember. Okay, so here, so we're choosing to do this derivative because explicitly writing it out, you'd have chain rule, but this part is going to be 0 because it's a rigid body. So as seen by the body, the mass should never shift. And you just end up with this, and because of the property that Ellen was talking about, the b frame derivative of omega b relative to n is the same thing as the n frame derivative. That's nothing but the inertial tensor times the angular acceleration vector, omega dot. Good, so now we plug this back up in here, and we solve for the angular acceleration. So omega crossed IC was just I omega, so you get omega cross, which is omega tilde I omega, and that gives you your classical form of our rigid body differential equations of motion, right? At least for the angular acceleration. If you want to track the attitude, what else are you going to have to integrate?
Kinematics.
The kinematic, the yaw pitch roll rate, or the DCM rate, or the MRP rate, or the quaternion rate equation relative to omega. So we get two sets of equations. This is just the kinetics side of it. There's also a kinematics side of it. Okay? Good. Now, if we have a principal coordinate frame that we've chosen one of those 24 permutations where this thing became diagonal, right, for a general shape, this always simplifies quite a bit, and you can write it in this nice compact form. And sometimes we use this, sometimes we use this. Just depends on what you're doing. So, yeah. Any questions on this? This is a single rigid body, H = L. When we move forward now next week into, reaction wheels and CNGs and variable speed CNGs, you're basically doing the same principle, just lots of it. And a bunch of bookkeeping and careful tracking of what rate relative to what rate, right? You have to apply all these things as we go there. There's a variety of solutions for torque-free motion. We're not discussing that much. 5010, we went through that quite a bit. In this class, we're doing mostly feedback control and then other ways to get equations of motion. So we're not going to delve too much into that. The power equation, this was the general form that we had earlier, where this was the rotational energy about it, which could be due to deformation, but also due to rotation. Now that it's rigid, the second part is only going to be due to rotation. There's no deformations. It's rigid. So what happens then is the translation of rotational energy, same thing as before, focusing only on the rotational side. The translational energy, that's really your orbit energy equation again, basically. We're not using that part. But the rotational energy here, R dot, as Joe said, is omega crossed R, dotted with itself. If you see something like this, you just know there's some magic trick formula that makes your life easier. So we use one here, how we can rearrange things, and this gives me this formula, where I have an omega outside. That's nice, because I can take it, omega's outside the body integral. Every point on a rigid body has the same angular rates. This part, I get to reverse the order, which gives me minus R cross omega. And again, the omega I can take out on the right-hand side. And the stuff in the middle looks just like the inertial tensor. And inertial tensor times omega is H. So kinetic energy is 1/2 omega dotted with the angular momentum. Or another way to write it is 1/2 omega transposed I omega, because momentum is I omega. And doing it in the matrix form, that's what you'd end up with. Good. So these two things. For 1D, what you might remember is 1/2, the inertia over 2 times angular rate squared. That's the 3D version of it, essentially. Now, it does rotate. Yay. Just in case you forgot what a rigid body tumbling looks like. Okay. So the kinetic energy rate equation, you can differentiate this. Especially this part, will lead to this term. The translational side, we've kind of seen earlier. We had force times the velocity where the force is applied is your power equation for just a particle. Right? So if you've got a particle sliding on a friction surface, you have some drag force acting on it. Whatever that drag force is times the velocity of the particle, that's the power being, that's the rate of change of energy of that dynamical system. Now we have same thing for the center of mass, that works. And for the rotational side, if you differentiate this, you can come up with this equation. And there's two ways to do that. You can either differentiate this, then you've got h dot is equal to L, plug it in, but you still have to do some simplification to get it into this form. Because there's also going to be, if you differentiate this form here, there's an h dot, but there's also an omega dot. And so somewhere you have to plug in the equations of motion that you had on the earlier slide. Same thing here, you can differentiate that. This is actually good practice, because we're about to see it in the Lyapunov stuff. Let's look at kinetic energy, right? If I have just V is equal to 1/2 omega transpose I omega. And omega, and I here is a symmetric positive-definite matrix. If I want to find V dot, what type of derivative am I taking of this scalar function? Franklin?
It's a scalar, so it doesn't have a frame dependence.
Yeah. So, doesn't matter. What about the right-hand side? Does it matter with respect to what frame I take the inertia tensor derivative or the omega derivative?
You have to make sure that all of your frames are consistent. So
Exactly. So if you have scalar quantities like energy that we're differentiating, just taking a time derivative, it's simply a time derivative. Don't ever write, ddt as seen by n or something. I'm just going to get all upset. Okay? So, this side means it really doesn't matter. That means on the right side, there's a disclaimer to it doesn't matter. Like, it doesn't matter which consistent frame you pick. Once you pick a frame, for all that math that you're doing, it better be that. If you have something else, plus omega cross omega, just making it simple, then I may pick here B frame, but for this math, I could pick N frame for all I care, right? For each scalar part, you get to pick individually. Like we've talked before, it's a linear operator. So, good. So here, what's the time derivative of this expression going to be? Anybody remember? Patrick?
Is it 2? Oh, not 2. The 2 cancels, just like omega transpose I omega dot.
Good. And for those of you who haven't done this kind of math, let's do it once explicitly. So this looks a lot like some constant over 2 times x squared, right? If you do classic calculus. And what's the derivative of this? X varies with time. You would have, so if I take the differential operator, you would have k over 2 times x dot. The 2's cancel, and you have simply k x dot, right? And because they're all scalars, you can rearrange any way you want. Here, if we go through v dot, I have 1 over 2 let me just write this out. And then I'm going to grill you guys. Okay, so if I use chain rule, so I'm doing dots here and here. I'm writing dots. That means what type of derivative have I taken here? Patrick. If we write a dot on a vector, what derivative are we taking?
Inertial.
Good. So is this a correct expression? Sarah? I just use chain rule to get from here to here.
Yes, if I is in the inertial, but
If is I constant as seen by the inertial frame? So, as seen by what frame is I going to be constant? Yeah.
The body frame?
The body frame. So let's just define dt of something, let's say r, that's just r prime. So prime is a body frame derivative, dot is an inertial derivative. Saves me lots of ddt's everywhere. So let's just go from v dot ends up being, if I did body frame, I'd have 1/2 omega prime transposed with I omega 1/2 omega I omega prime. This, hopefully everybody agrees, would be correct, right? Because there's no I prime, there's no derivative of the inertial tensor as seen by the body frame, because that's always constant. But, Elena, how does omega prime and omega dot relate again?
They're equal.
They're equal. So this is, in fact, correct. But just if you're doing this trick and you're going from here to here and putting dots everywhere, be bloody careful that you understand what you're doing, right? Because if you're really taking inertial derivatives on everything, you know, if you have a tracking problem, this is omega b relative to r, and you're just adding dots on this, what are you really taking, you know? If you're not sure, do this stuff first, and always pick the frame that keeps the inertial tensor fixed. Otherwise, things get really crazy, typically, right? Then you can do that. But this is correct. And now, Patrick gave us this nice simple form. Because in 5010, we had this trick that we said, okay, if you have x transposed I times x, and I is symmetric, take the derivative, it just gives you 2 times x, I, x dot, right? That's essentially what we got out of this stuff. Why does this collapse back to this?
It's a scalar. And so
It's a scalar.
So you can switch to the transpose. And
another way to think of it, this is omega dotted with h, right? This part is h, and this is h transposed on that. And the dot products commute, a dotted with b is b dotted with a. Or in the matrix form, as you can see here, if the answer is a scalar, then you can always transpose the scalar. And a 1 by 1 is still a 1 by 1, the same thing, but the order of the matrix multiplications reverses, right? So so 1 can become this. So this is correct, or equally correct, you could have put a dot over here and have this as the undotted omega. That's also correct. We tend to have this form. Why? Why do we like this form?
Equations of motion.
Yeah, I omega dot is exactly what we need for equations of motion. You're going to be lazy, right? That's no, with that step, I can just plug and chug the stuff right in. So that's how we happen to use that. But technically, you could go either way. So if you're rusty on this kind of a math, definitely you need to practice, because we'll be doing a lot of this. This is how you want to solve it. You don't want to have to do all these expansions every time. But if you do this, be aware of the subtleties that go on taking these derivatives to get to that step. Okay? Nice. Okay, so I'll let you figure this out on your own, how to get to the power equation from here to here. There's 2 different paths you can take. They all lead to the same thing. But just as with force, what people remember is more the force stuff. Force dotted with velocity gives me the power being applied to the system. From an angular sense, it's torque dotted with angular velocity. All right? And this is the force acting on the body relative to the inertial. This is the angular torque acting on the body relative to the inertial. And this is the inertial velocity. That's the velocity of the body relative to inertial. Omega is the angular rate of body relative to inertial. We'll see similar equations later on appearing when we do the reaction wheels and CMG torques and so forth. It'll have the same form. It's the torque between the CMG frame and the body dotted with the angular velocity between the CMG frame and the body. You know, it'll have the same kind of a thing where these other letters become placeholders. But it always works out. And if you want work between time, you can integrate this or replace this with a position or rate angular stuff if you wanted to, but that's kind of the classical thing. Okay, so we've spent quite a bit of time. Yeah, quite a bit of time. Nonlinear control. Let's look at some highlights. With a linear system, and it's strictly stable, where are the roots on the linear system?
Left half plane.
Left-hand plane, right? Negative real parts in the roots, right? If it's not strictly stable, it's only marginally stable, where are some or all of the roots? Yep, imaginary axis, right? If it's unstable, where are the roots?
Right.
Right-hand side. We don't want any right poles. They'll all have the poles of your characteristic equation. And if you're fuzzy what a characteristic equation is, you definitely need to go look it up. Different ways to get to that one. But that's for the linear system. So if it's stable, it is stable. If it's strictly stable now, everything's on the left-hand side, am I asymptotically stable? Let me throw in some nonlinear terminology.
It's strictly stable?
Yes.
Yes, you're asymptotic.
Right. So if it's strictly stable, it will get there. Is it exponentially stable?
Also, yes.
Right? Because that was a difference in nonlinear systems. You can be asymptotically stable without being exponentially stable. And we'll review that again, right? And are we always bounded if it's strictly stable? Is there a bound where you're always guaranteed you'll get beneath that? Yes. So then I say linear systems, once you're stable, that's it, you know. That's as good as it gets. There's no other differentiation to have to do, which really simplifies your life. But then you can worry, linear control is great because you can look at performance, are you over-damped, under-damped, critically damped, there's all these different, what's the settling time, there's all these metrics that we have that are very useful to kind of design. Because just being stable, that's the beginning of your job as a control engineer. You still have to worry about performance. Am I going to get there in 1 day or 1,000 years? You know, your sponsor will care, let me tell you. So, you know, performance is also another thing. And linear control is fantastic for performance. Predictions, it's harder to do with nonlinear systems. Nonlinear systems, we can do stuff that's guaranteeing global stability. With performance, we often go back to a linearized version and do that kind of stuff. Good. So we have different things we want to investigate. The state vector. What is that? For the attitude problem, purely rotational kinematics. Benjamin, what goes into the state vector?
For rotational kinematics, I would put the attitude angles.
So MRPs, for example, sigma 1, 2, and 3. What else?
Quaternions.
You would put MRPs and quaternions?
No, I mean one or the other.
Okay, so we picked one. That's it?
For attitude, or for the complete...
So this all comes down to what is this n, right? How many do we need for a system? Let's start out simple with the spring mass damper system. What is the n that you need? What's the size of that state vector? 2, right? It's a second order differential equation, so I have to track x and x dot. It's driven by x double dot.
6 in this case.
We need 6. So rigid body, it's 3 degrees of freedom, but it's also a second order differential equation. All mechanical systems are second order differential equation. So you've given me 3 for the attitude. What's the other thing we're missing?
Angular velocity.
Yeah, which we tend to use omega. We don't tend to use, you know, MRP rates or quaternion rates. We use angular velocity. So yeah, that's what would be in there. So this is just written out in a classical control theory formulation. And now you have a non-autonomous system. That means this system actually explicitly depends on time. There's a servo that just drives a piston back and forth and doesn't care what else is going on, and that's just a time input, right? This position will vary like this. That makes it time dependent. And then there's also autonomous systems, which means it doesn't depend on time. We like this. This is much easier, but we'll talk this class also a little bit more. 5010, we hinted at this. We'll talk a little bit more about using Lyapunov theory with non-autonomous systems, time-dependent ones, right? Orbits, you often have this problem because you're launching, you have this much fuel, how can I intercept that asteroid before it hits us? Now it depends when you launch. Are you going to converge? That converging now becomes a function of when is this launched and so forth. Question? No? Keith?
For a state vector, does it always need to be a minimum set? So it always has to have 6 parameters?
No, that's an excellent question. So if we have a redundant, let's say you use quaternions, Benjamin. Now we have 7. Do we just throw away one of the omegas? What do we do if we have 7 instead of, because you said we could substitute MRPs with quaternions.
There must be a closing relation somewhere.
Right. So you have to enforce a constraint. Right. Now you can integrate these, and your equations of motion, if you give it an omega, will tell you how your quaternion rates evolve and how you can integrate them. But in real life, what happens with the quaternions when you integrate them numerically? Are they going to continue to have unit length? They're going to slowly deviate, depending on the quality of integration technique that you're using. So you might have to worry about enforcing constraints. So you can have redundant formulations here, and the equations of motion work just fine. I can deal with a 7-dimensional or 15-dimensional representation of it. Just the equations, of course, have to satisfy all the inherent constraints. I don't have a 7-dimensional problem. It's really just 4. I've chosen to use 4 because there's some benefits. But then in the integration, you'd have to make sure after every step you might renormalize your quaternions to make sure they don't grow unbounded. Yes?
Is there a better way to normalize the quaternions than just dividing the newly computed quaternion by its norm?
That's typically the way I've seen it done. Yeah. If you have a DCM, there's some nearest orthogonal matrix stuff that you can look up. No, with the quaternions, basically, it's a very small value. You just renormalize it to keep it bounded. Yeah. Which is an error source, of course, but still, everything has error sources. U, generally written, this is our control that we pick, and this G function could be linear, and you will see we have some controls we developed that are linear, that guarantee stability in a nonlinear system, or this could be a nonlinear function, depending on what we're doing and how we're doing. This is generally written. Then the closed loop dynamics is, what are the dynamics once you plug in this U? Somehow U has to appear in our equation. You know, what's the reaction wheel torques? What's the CMG steering? What's the thruster torque and so forth that happens to the system. So that's our closed loop dynamics. So an equilibrium state, that is simply a state where these state rate functions go to 0. That means here, putting this pen on the table, and it's finished wobbling, that's an equilibrium. It has a certain position, and it has a rate. The rates here have to be 0, and then my rate accelerations are 0, and my position rates are 0. So there's no, it's not going to move, right? That's an equilibrium. I may move it over here, and this is another equilibrium once it stops. There you go, right? That's simply an equilibrium of the system. And for attitude dynamics, we do the same thing. There are naturally occurring equilibria, which we've seen. There's relative equilibria if it's relative to a moving frame. With torque-free motion, we saw that spinning about axis of major inertia was actually stable. And if you're perfectly spinning, it just continues. All the rates, accelerations go to 0. So that's also existing there. So that's good. From a feedback control perspective, we often get to choose. Maybe having the satellite do this motion isn't a natural thing. So now I get to choose a control which makes it converge to this. Essentially, you're introducing an artificial man-made equilibria, right? And you're forcing with these reactions and how they're firing and what they're doing is that this craft will actually stabilize onto that motion. Just like this pen is stabilizing on a table. I don't like the natural dynamics, so we get to modify it. That's what feedback control does. So quick definitions. Let's go through here. Neighborhood. Billy, what does a neighborhood mean?
An area of state vectors.
Right. So we've got a state vector, which could be a 3D vector, it could be a 6D vector. But in the end, how do we define proximity to that in that neighborhood? These neighborhoods had a particular shape. That's what I'm going for.
Hypersphere?
Yeah, there's some sphere. So hyperspheres, it's multidimensional stuff, right? Because we use which norm, Joe? The L2 norm, right? So that's typically how we define closeness, proximity. That this vector here minus this vector there is that close. In a scalar sense, you're doing the L2 norm. The difference is sum squared has to be less than something. So it's like making is it within a hypersphere? And that's kind of what we're writing here. So this minus this, and this norm is the L2 norm. That gives you this ball-looking, this hyperball-looking object, right? So we have a definition of are we in, are we close? And right now, everything we're doing in the up and up is all based on L2 norms. So everything's here based on the ball by concept. And that's important as far as we can sometimes guarantee that it'll converge if you start within this area. But if you're starting outside, I can't say if it will converge or not, right? And it may, in fact, because the true conversion regions in nonlinear systems aren't typically balls. There might be something that looks like an eyelid or a big open area, or it just depends. But we can approximate them to the best with the Lyapunov theory with balls. Lagrange stability. Joanna, what does this one mean?
That the neighborhood would stay within bounds.
Do these bounds depend on the initial conditions?
Yeah.
You want to try again?
No.
No, but that's the key thing with Lagrange stability. It's boundedness. Think of a spring mass damper system. If you just have a spring mass damper floating in space, things will settle and the spring settles to the origin, right? If you put this system now in a gravity field and you got a spring mass damper system, we will settle but never at the origin. It always settles at an offset, right? Where the spring force balances the gravitational force, essentially, right? But that offset, that's it. You always settle at, let's say, 1 foot offset. It doesn't matter if I start out with small deflections or start out with huge deflections. I always settle in the same place. That's a boundedness that we have. It doesn't depend on initial conditions. You will always be within. You can't fiddle anything with your gains and stiffness and damping. You will always settle in 1 meter, right? That's Lagrange stability or boundedness. That's what we're saying. So there's a ball, but it just doesn't depend, this delta and this stuff doesn't depend on initial conditions. Lyapunov stability, on the other hand, again, we have a final ball, a final area we're converging to, but here, Gabrielle, does that final ball size depend on initial conditions?
Yeah, you start in one neighborhood and you...
Yep. So this neighborhood now all of a sudden depends, this epsilon depends on the initial stuff. There's a coupling, a relationship between them. And the simple example to consider here is a spring mass system. A spring mass system will always have an oscillatory motion. It'll never converge. But if you say, I want to be, an epsilon is going to be 1 meter, I can deflect my spring 1 meter at rest, let go, and it'll bounce, and it'll always stay within 1 meter. If I want to deflect, if I want to stay within 0.1 meters, I deflect it just a little bit, 0.1 meters, no speed, let go, and it's going to continue to bounce 0.1 meters. You can make this arbitrarily small, but once you let go, it'll never converge to 0, right? That's essentially what Lyapunov stability looks like. It's like a spring mass-like stability guarantee. You know, I will get within some region where I can guarantee this stuff, but I won't ever converge. If we do converge, what do we call that kind of stability, Franklin?
Asymptotic.
That was asymptotic stability. So here the final ball shrinks to 0, and it does it. Now, all these stability proofs I just mentioned were local stability. That means there's some initial neighborhood that you can guarantee. If you start out within 1 meter, things will converge. If you start outside 1 meter, you're on your own, right? It may converge, it may not. In fact, it may diverge. There's examples with that, with the dumping equation, which I'll show you. Actually, that's, well, global stability. That's an example here. You've small departures, I'm still stable. But at some point, if I have big departures, things go off, right? So this is the thing about local stability. And global stability just means it's good for any initial conditions. I'm guaranteed that all these stability properties hold, right? So with nonlinear control, we have Lagrange stability, Lyapunov stability, asymptotic stability, and each one of those is global or local. And the other thing is exponential stability, which I don't cover much in class, but you have to look at the, you know, there's some decaying asymptotic function. And that's one that you have to do as well. That'll guarantee how fast you perform. Asymptotic stability just means you will get to 0. It doesn't tell, you may get close to 0 very quickly, and then it may take eons, literally, to converge. You know, and that's still stable, but it's not a nice performance. If you have it exponential stable, you know every half-life you've cut it in half, the error, you know, and it will continue to do that. The Lyapunov stability doesn't guarantee you that. So this is hierarchy of stuff that we have to use to do feedback control. Okay, we'll end here. I'm over 3 minutes, so we'll pick up here on Thursday and continue on with all the stability definitions, wrapping up this stuff.
What's this present? Well,